Hello everybody, welcome to this Quintus Technologies webinar focused on hot isostatic pressing for orthopedic implants. My name is Magnus Alfors, I'm a hip application engineer at Quintus Technologies. Here we can see the agenda for today. I will start with an introduction to Quintus Technologies and the fundamentals of hot isostatic pressing or hipping. Then I will discuss hipping of orthopedic implants, the modern hip systems of today, and how to source the hip process. And in the end, we will have a question and answer session. So please submit your question into the webinar tool and we will try to answer as much as possible in the end of the session. Okay, so we start with a short introduction to Quintus Technologies. And Quintus Technologies, we have our roots in the Swedish company ABB, formerly known as ASEA. And we are, however, not a part of ABB anymore. And it was the innovation in the 1950s at ASEA of how to make synthetical diamonds that led to us working with isostatic pressure technology today. Today we make hot and cold isostatic presses for material densification, and we also make sheet metal forming presses that also uses isostatic pressure to perform the forming. Today we are around 220 employees worldwide, and we have our headquarters in Västerås, Sweden. Our Asian office is in Shanghai and the US office is in Columbus, Ohio. Since we started in the 1950s, we have delivered over 1900 high pressure systems worldwide, and our history of innovation have led us to 120 active patents today. So now I want to talk about the fundamentals of hot isostatic pressing. And the definition is to apply a pressure distinctly higher than the yield strength of the material at the hip temperature. So it is a process with high temperature and high pressure. And at this high temperature, the flow stress of the material will be very low. So the stresses we induce with the pressure will be higher than the flow stress. So the material will plastically deform to, for example, collapse internal porosity in materials. And hipping is used then for densification and elimination of internal defects in cast material, additive manufactured material, and sintered material. Pretty much any material containing internal porosity and defects. The mechanism that's working during the hip process is mechanical deformation, creep, and diffusion. And the isostatic pressure condition is we are using an inert gas as pressure medium, and this gas is then pressing on the components on all surfaces in all directions with the same pressure. If we then look at as printed, as cast, or as sintered materials, there will be some internal defects. This can be lack of fusion defects in powder bed fusion material, residual sintering porosity for binder jet and MIM, solidification shrinkage porosity in castings, as well as gas porosity and internal cracks. And what these internal defects will do is that they act as stress concentration and crack initiation points in the material, and this can negatively influence your material properties. So the main purpose of hipping is to eliminate these defects, so you eliminate the stress concentration and crack initiation points. And this will give us improved material properties. For example, improved ductility and fracture toughness, better creep properties, and especially improved fatigue properties. We normally also see a reduction in the scatter of properties. So since there will be a natural variation in between different components or different batches of components in internal defect porosity, if we eliminate that, we normally see a reduced scatter in the properties. So we get more predictive properties and we can hopefully design the components towards higher strengths. You can also get improved quality of machined and polished surfaces by using HIP. If we look on the bottom right here, we see on the left picture there, we see a cast tube that's been machined on the inner surface. And as we can see, some of that internal porosity has been revealed into the machined surface. On the right of that picture, we have the same type of cast tube, but it has been hipped before machining. Since we have eliminated porosity, we have 100% solid material, we don't get any surface porosity in that machined surface. And this can be quite important when it comes to medical implants. For example, a knee joint like this, we definitely want the sliding surfaces to be very smooth and polished. So we don't want any surface defects in this part that would harm the sliding application. And here's an example of improved fatigue properties by HIP this is for an electron beam powder bed fusion Ti64 material. So if we look at the curve right here, we have the as printed material, and right here we have the data for the same material that's been hipped. And to compare these, I put some lines here at an amplitude stress of 600 megapascal. And as we can see at this stress level, this as printed material will last around 90,000 cycles. But with the HIP material, we get around 4 million cycles at the same stress level. So this improvement in fatigue properties is one of the main reasons why hipping is used. So now we know what hipping is, then I will talk a little bit more about hipping for orthopedic implants specifically. So hipping is widely used for orthopedic implants for joint replacements, and the reason is the improved material properties, and this is to ensure desired performance, quality and lifetime of your implant, and especially to prevent catastrophic failure of the implant inside the human body. And the types of implants we're talking about are the structurally loaded ones, so typically the joints, etc. So we talk about hip implants, knee implants, shoulder, spine, ankle, wrist, dental as well. Manufacturing methods are casting, additive manufactured material, metal injection molding, MIM, which is common for dental applications. And all of these processes typically have some internal defects or porosity in the as manufactured condition. And this is something we want to eliminate with the HIP process. Materials are cobalt chrome alloys, for example F75. We got titanium alloys where Ti64 is common, and then the stainless steel like 316L. And here's an example to show the importance of good and also predictive material properties for your implant. So the X-ray images we see here actually belong to a Quintus colleagues of ours, mother. And this is a stainless steel implant for the upper arm that was fractured. And this implant was supposed to stay permanently in the patient here, but it failed after just 7 months. So she had to go in for a resurgery. And this, of course, caused a lot of pain and inconvenience for the patient, and it also adds a lot of cost to the healthcare system. Additive manufacturing is growing fast as production method for implants, and one of the reasons are the design freedom. We can make quite complex geometries in an easy way. For example, it's possible to optimize the surfaces of the implant for bone ingrowth. And here we can see an example of these quite porous surface that's possible to produce, where that will promote the bone to grow into this structure, so you get a good fixation between the implant and the skeleton. That will prevent the implant loosening up after a few years, which is definitely something we want to prevent. An application that's getting more and more popular is the made-to-order patient-specific implants, where you can design the geometry of the implant based on the X-ray imaging of the patient. So you get a really good fit from the implant with the patient's geometry. And this is enabled by AM since it's easy to make new designs every time. Also, the made-to-order patient-specific implants, it's very important with a short lead time. For normal standard implants, the healthcare system will have these on the shelf ready to go when needed. But of course, if it's a made-to-order implant, the lead time to get that implant made is also the wait time for the patient. So it's important to try to reduce time in the printing, hip and heat treatment, sterilization, and transport to get the implant to the patient faster. When it comes to hipping of AM parts, normally the parts are removed from the build plate before hipping, and you place these implants into the hip furnace separately. However, it is also possible to hip on the build plate, to let the parts stay on the build plate and then put the entire build plate into the hip system and hip as is. By removing the parts from the build plate, it's possible to get a better fill ratio in the hip. But loading the entire build plate into the hip system, you can normally reduce the number of touches in the process, so you can run the whole thermal processing of the build plate and the parts, and then take the parts of the build plate in the end. We can often see that the microstructure on additive manufactured material are quite different from the typical traditional cast and wrought material. However, most hip and heat treatment protocols are developed for cast or wrought materials. So we have seen through our studies together with universities and other partners that it is possible to optimize the hip and heat treatment protocols to the AM process to get more optimal final properties. And here is an example of optimizing the hip process for AM material. Here we're looking at the powder bed fusion Ti-6-4. And the standard cycle for this material that's used typically in the industry today is 900 to 920 degrees Celsius, 100 megapascal at 2 hours. And this cycle is developed for cast Ti-6-4 a long time ago. So one question is, are these parameters really optimal for additive manufactured, since the starting microstructure often are quite different? And we did a study together with RCAM a few years ago to look at if different hip parameters could lead to better properties. And our approach was looking at lower hip temperatures to try to minimize the coarsening of the fine microstructure that we have in the powder bed fusion material that gives quite high strengths. And we can see the results here on the upper right. We have the yield strength of the material here, and these bars show the yield strength of the material that's been treated with the standard hip process at 920 degrees Celsius. And then when we go to the right here, we see that we have decreasing hip temperature. So we have 880, 840, and even 800 Celsius here. And interesting to see here was that the strength increases with decreasing hip temperature. So we concluded that 800 Celsius, 200 megapascals, and 2 hours gave the highest strength. And if we look at the elongation down here, we can see that the elongation are pretty much the same for all variants. So just by tweaking the hip parameters a bit, reducing the temperature, increasing the pressure, we could get higher strength at the same ductility level and what was overall better properties. In a different study, we also saw that we got better fatigue properties with this hip cycle compared to the standard cycle. And now I want to talk about the modern hip systems of today. And we have put a lot of time and effort in during the last couple of years to develop and improve the equipment for hot isostatic pressing. So today a hip system is quite user-friendly, it's space and cost efficient, it's easy to operate and maintain. We offer a variety of different sizes of hip systems, so you can easily find a hip system size that's suitable to your production volumes, parts per year. And one really cool thing is the rapid cooling capabilities that we offer with our hip systems today. We can do rapid cooling and quenching with the gas inside the hip system at the hip pressure. And this quenching is as fast or faster as the typical high pressure gas quenching in a modern vacuum furnace. And this rapid cooling gives a significant reduction in the total cycle time. And this then gives a high productivity of these systems. The rapid cooling also makes it possible to combine hip and heat treatment in one cycle inside the hip system. And I want to talk more about the combining hip and heat treatment that's possible with these modern hip systems. And here we can see how a conventional post-processing route could look like for an AM part today. So we might have a stress relief step, and then we probably have a hip step after that. And then we could have a solutionize and quenching or cooling step, and then probably an aging or tempering step after that. So the main purpose of combining hip and heat treatment is to eliminate process steps and also eliminate the transfer operations in between these steps. All these steps are typically done in different equipments. If you're outsourcing the process, it's not uncommon that the processes are done at different sites or at different suppliers. So the main purpose is to combine these steps into one cycle performed in the hip. So it could look something like this. We have a stress relief, we combine the hip and solution treatment, we do the rapid cooling in the hip, and then we do the aging and tempering also in the hip. However, it is also possible to take the parts out at this point and do the aging and tempering in some other type of furnace. So the benefit of this, as mentioned, eliminating process steps, eliminating the transfer operations in between them to shorten the processing and lead time. We also get a reduction in energy consumption, which is interesting in today's green society. Since in this case we're heating up and cooling down the part 4 different times, while here we can do it either 1 or 2 times. A benefit from a more metallurgical point of view is that in this process we are minimizing the time at elevated temperature, which can be important for minimizing grain growth in the material. And here we have an example of combined hip and heat treatment for the cobalt chrome alloy F75. And looking on the left here, we have a specification, which is a recommended post-processing route that I've taken from Arcam's website. So here we can see they recommend a hip cycle first at 1200 Celsius, 100 megapascal for 4 hours. And then after this hip treatment, they recommend a homogenization treatment at a similar temperature, 1220 Celsius, in vacuum, also 4-hour soak time. And the reason for this homogenization step after hipping is that they have a requirement on a minimum cooling rate. This material has to be cooled fast enough to avoid formation of carbides on the way down. And this cooling rate corresponds to 58 Celsius per minute or 105 Fahrenheit per minute. And that type of cooling rate is easily achievable in a modern hip system today. So with rapid cooling hip systems, there's no need to do this homogenization treatment after hipping. You can do the hip step and then do the rapid cooling from here instead. So in that case, you would do 1 cycle instead of 2, use 1 equipment instead of 2, and spend 4 hours at temperature instead of 8 hours, and that's very beneficial. Here I want to show an example of the high productivity of these modern hip systems today. So in this case, I have chosen a knee implant to look at, a small calculation study here. Material is the cobalt chrome F75 alloy, so the hip cycle is 1200 Celsius, 100 megapascal for 4 hours. The production conditions I've assumed to be 24 hours per day, 5 days a week, 48 weeks per year, and with 90% uptime of our hip system. Then I looked at 2 different products of ours, the QIH15L and the QIH48. Here we have the implant. We can see the geometry and the size of it. I've represented it with a cylinder here. So when calculating how many I can fit in the furnace, I assume that they're not touching each other, so quite conservative calculations. And in the table here, we can see the size of the 2 different hip systems. So the 15L has a 7.3-inch diameter of the hot zone of the hip furnace, and the 48 has a 14.8-inch diameter. So in the 15L, we can fit 90 implants per cycle, and in the 48, we are just above 1,000 implants per cycle. The total cycle time with this alloy is then around 8 hours, with a little bit longer time for the larger system. And this is calculated with the rapid cooling. If a hip system without rapid cooling would be used here, the cycle time would be close to double this number. So looking at the annual hip capacity with these systems for this part, we get around 58,000 implants per year in the QH15L. And with the QH48, we get around 611,000 implants. So these are quite high numbers, considering that these hip systems belong to our compact series. So these are relatively small hip systems. And now I want to talk about sourcing the hip process. Today there are mainly 2 ways to acquire the hip process. Either you use an external service provider where you would send the parts, get them hipped and get them shipped back. Or of course you can operate the process in-house. Today most orthopedic implants are hipped by external service providers. And for your information, there are 4 new hip service providers in the US that entered the market in 2019. These are Stack, Paolo, Acrobracing, and Heat Treat Mexico, in addition to the already existing service providers. And we're quite excited to see this because it gives the customers a much better opportunity to get modern hip capabilities. There are also new hip service providers in Asia and also Europe, Flame Spray and Pressix being 2 of them. But now I also want to talk about insourcing the hip process, and we see that this is becoming more interesting. Some implant manufacturers have already invested in hip equipment to bring the process in-house, and one of the reasons for that is the development within hip equipment during the recent years, as I already talked about. And there are some benefits with insourcing the hip process, and some of them are listed here, and I will go into detail on some of them. So first of all, having the hip process in-house, you can shorten the lead times. This since you can eliminate the time of transport to and from the service provider. Also, you don't have to consider the lead time at the service provider. And if the parts have after following heat treatment step today, that could potentially be eliminated if you run a combined hip and heat treatment process in your in-house operation. There's always some risk when sending parts outside of your site, and these risks of delay or damage of parts during transportation will of course be eliminated if you have your process in-house. Control over quality is another benefit. By having the process in-house, you will develop an expertise and know-how on how to best run the process for your specific parts and needs for optimal outcome. And you have the control in your own hands to avoid mistakes or avoid the potential non-conformities, such as surface oxidation, alpha casing of the surface of the parts, hip parameter deviation, etc., whatever that can happen. You would at least have your own control over these kind of things. Down here on the right, we see a picture on a micrograph of a Ti64 specimen. And on the surface here, we see that we have a layer of alpha casing right here, and this has been formed during hipping. So it is important to have control over your oxygen and moisture levels to be able to prevent this. The insource option also provides a great flexibility in planning. For example, time-critical deliveries can get fast-tracked through the internal schedule. For example, patient-specific devices could be done that, so it can be treated in hours instead of days and weeks. Also, if you operate the hip process in-house, you will not be limited to the standard coach and cycles that the service providers might offer. So you have the possibility to develop your own hip and heat treat protocols that are optimized for your material and application to get the optimum properties in the end. Of course, you can run in-house R&D to improve and make new processes for new applications and materials. Having an in-house hip system with high utilization rate will give the lowest production cost in the end. This since you can eliminate costs for transport, insurance, profit of the external company, etc. There will also be indirect cost savings from improved quality control, planning, delivery times, etc. So before we go into the question and answer session, I just want to summarize this presentation. As I talked about, hip is widely used for orthopedic implants. This because it eliminates internal defects, improve the material properties, and ensure quality and performance of the implants. Additive manufacturing is a fast-growing technology production method for implants, and as I showed, hip and heat treatment protocols for cast and wrought materials might not be optimal for AM materials. So there are some optimization potential out there on the hip and heat treatment protocols for AM parts. Modern hip systems have today rapid cooling capabilities. This can significantly reduce the cycle time, which increases the productivity of the hip system. The rapid cooling also makes it possible to combine the hip and heat treatment step into one cycle made in one equipment to eliminate process steps and get a more lean production. Insourcing the hip process can be beneficial. you can get shorter lead times and you get a flexibility in planning. A lower total production cost and control over quality and risks is a benefit. And you can also use optimized HIP and heat treatment protocols to get the best properties out of your material. So with that, I thank you very much for your attention, and stay online because we start a question and answer session right now. Thank you.